Hello dear students, are we all braced up to understand the application part of the chapter sets? Because just understanding the theory and not getting the very flavor of the application is halfway done. So let's start with the very CBSE pattern questions which are frequently asked. The very first question is, which of the following sets are empty sets? Let us try and examine. There are 5 distinct sets given to us. We have to basically see which are the sets which have no element sitting inside them. Let us look at the first set. The first set is set of all even natural numbers which are divisible by 5. First of all, if a number is divisible by 5, it is going to be written as 5 into something. That means it will be coming in the table of 5, which means it will be a multiple of 5. Therefore, in order to understand if there is any natural number which is divisible by 5, we will have to go to the table of 5, which means the multiples of 5. If I start with the multiples of 5, 5 ones are 5, 5 twos are 10, 5 threes are 15 and so on. I am getting many natural numbers which are divisible by 5. The first part says to collect all even natural numbers which are divisible by 5. As I said, 5, 10, 15, 20 and so on are so many natural numbers which are divisible by 5. Is among these any natural number which is even and divisible by 5? Yes, of course. 10, 20 are even natural numbers which are divisible by 5 because they are multiples of 5. And therefore, we have at least one element, say 10, sitting inside set number 1, and therefore first set is a non-empty set. But we are supposed to mark the sets which are empty, and therefore number 1 is not the correct option because it is a non-empty set. Moving on to the second set, which is the set of all even prime numbers. This is where I am going to tell you about the only even prime number among the set of all prime numbers. Where do prime numbers start from? They start from 2, then go to 3, then go to 5, then go to 7 and so on. If you observe carefully, apart from 2, all prime numbers are odd numbers. The only prime number is 2. And therefore, set of all even prime numbers is actually a singleton set 2. This is what my set 2 is. It is singleton 2. And therefore, this set is also non-empty. If I move on to the third set, and therefore 2 is not correct also because I have to answer which sets are empty sets. My set 2 is non-empty set. Going on to the third set, it is saying collect all those numbers whose square is giving you 2, and those numbers should be rational numbers. Suppose I take my third set. I want all x such that x square minus 2 is a 0. This means x square is equal to 2. But this can only happen if x is plus root 2 or minus root 2. And in both the cases, it is an irrational number. So, for x square to be equal to 2, x will have to be either root 2 or minus root 2. That means both of them are irrational numbers. Therefore, there does not exist any rational number such that on being squared and getting 2 subtracted from it, there is 0 what is coming. And therefore, there is no such x. Therefore, my set C, which is the third set, is actually an empty set. This set is empty. what I start is the fourth set, which says x is a natural number such that x is strictly less than 8 and simultaneously x is strictly greater than 12. And x is a natural number that is given to us. So in order to understand the fourth option, let us try and draw a small number line. If suppose on the number line, somewhere here I have the number 8, beyond it somewhere I have the number 12, obviously to the right of 8, I am asked to collect numbers which are strictly less than 8 and they should be natural numbers. And therefore, numbers like 7, 6, 5 and so on come in this category. Also, we are supposed to collect numbers who are strictly greater than 12 and therefore numbers like 13, 14 and so on also come in this category. Is there any number right now who is less than 8 also and greater than 12 also? Of course not. This is absurd. Therefore, no such natural number exists who is simultaneously less than 8 and greater than 12. This set, my friends, is also empty. Let us try and see what the fifth set is. All those x such that x is a point common to any two parallel lines. In set number 5, suppose you take any two parallel lines. For that matter, any two parallel lines, just consider the tracks of the railway train, and these two parallel lines can never meet. The moment they meet, that will be the point which will be commonly occurring in both the lines. But because parallel lines, they never ever meet, therefore there can be absolutely no point common to both the parallel lines. And therefore, even here, there does not exist any such point common to any two parallel lines. Set number 5 is also empty. Therefore, set number 3, set number 4 and set number 5 are empty sets because there is no element satisfying the rule by which these sets are formed. Set number 1 and set number 2 on the other hand were empty sets and we understood why. Quickly spend some time with this question and then we would move on to our second question. What does the second very question ask us to do? Let me give you some time to understand this question. Now we have to unfold the very mystery what the second question is trying to say. Let us read it and understand it all together. The second question basically says, which of the following sets are finite and which one of them are infinite? If I consider the first set, it is the set of all concentric circles in a plane. Do you know what a plane is? Let me show that to you. If suppose I consider my first set, which is the set of all concentric circles in a plane, I am going to show you a plane here. This is my plane. Basically, this is the x-axis and this goes to be the y-axis. This is called the Cartesian plane or the Argand plane also. If I try and make concentric circles, the very simply which I can start is, I am going to take origin as the center and start making the concentric circles. Suppose I make the first circle approximately, then another concentric circle to this circle, and then another circle, and then another circle, another circle. I can go on and on and on. This process is never stopping because my plane, which is the Cartesian plane, is endless. It is unbounded, it has no boundaries, and therefore these circles will just keep increasing in the radii, and therefore there will be no stop to the number of concentric circles which we can find to put in set 1. Therefore, very clearly, set number 1 is not a finite set. It is an infinite set. I am writing I before the set who is infinite. Let me bring you to the next set, which is a set of letters in the English alphabet. If I try and decode my second set, it turns out to be the set of all letters in the English alphabets which start with A, B, C and go till Z. There are 26 of them. 26 is a number which is superbly finite, and therefore this particular set, set 2, has cardinal number equal to 26. This is what makes the set finite, and therefore my set 2 is very much a finite set. Set number 3 says collect all those natural numbers which are greater than 5. In order to unfold my set 3, let me again draw a number line before you. If this is the very number line and suppose 5 is sitting somewhere here, I have to collect all the natural numbers which are strictly greater than 5. For that, I'll have to say 6, 7, 8, 9, 10, 11, 12 and so on. This list is not stopping. Numbers which are strictly greater than 5 are 6, 7, 8, 9, 10 and so on. This particular set, its cardinality cannot be found because the process of labeling the terms with the help of natural numbers is not coming to an end. And therefore, set number 3 is again infinite set. Set number 4 says, inside me are all those natural numbers who are strictly less than 200. Now, in set number 4, we have to collect natural numbers strictly less than 200. Now, this is funny because it seems to be that the set is infinite. In fact, it is finite because again, if we consider the number line, natural numbers start from 1. They don't go beneath 1 or less than 1, and we can go up till 200. Natural numbers between 1 and 200 can be 2, 3 and so on till 200. From 1 to 200 there are 200 natural numbers. Suppose in the case of n there would have been bold Z written. In that case, question would have been collect all those integers which are less than 200, and that would have been an infinite set because in that I will be allowed to go before 1 also and collect -1, -2, -3 and so on till minus infinity, which itself would have made the set infinite. But here, because we have bold N written here, therefore, this set is finite because it has 200 terms in it, starting from 1 going till 200, or not even 200 because 200 is not allowed. It is not written equal to 200. Therefore, we can only go to 199 and the cardinal number becomes 199 for set number 4, which is a finite number. And therefore, set number 4 is again a finite set. Coming to set number 5, it says inside me are all those integers which are strictly less than 5. The same scenario which I was trying to say. Suppose you have 5 over here in the number line. Integers which are less than 5 are 4, 3, 2, 1, 0. Not just these, -1, -2, -3 and so on. Because the negative ones are also allowed to be taken here, the collection given is integers. And therefore, all the integers less than 5 start from 4. 4, 3, 2, 1, 0 and go on to the negative real axis. Therefore, this set is also pretty much and very much an infinite set. Going to set number 6. Set number 6 is all those reals such that x is strictly greater than 0 and strictly less than 1. Do you remember where have we seen this set? If I remind you, set number 6 basically is the very definition of open interval AB, because open interval AB was all those real numbers such that x is strictly greater than A and strictly less than B. Instead of A, I am given 0. X is strictly greater than 0, and there is 1 which is the next end point which is given in place of B. And therefore, what my set number 6 is nothing but equal to 0, 1. This is what my set is, and this, my friends, is very much an infinite set. All the real numbers between 0 and 1 cannot be counted, because I told you that all the real numbers are pretty much dense within each other. Pick up any two real numbers as close as you want, you will find another real number sitting in between, and therefore assigning natural numbers to them was a task which was not possible, and therefore their cardinal number could not be found, and this set is again an infinite set. Spend some time again and do this question again so that you hold a firm grip upon it, and then we would move on to the third question. Now we are in a position to deal with the third question, which is frequently asked in the CBSE exams. Quickly take a look at it. This question is related to the basic set theory principles. It is giving you set A, set B and set C, and it is finding you all sets which are behaving in a certain manner. Let us start with the solution set. Solution set basically says that firstly, in order to find subset X of B, of C, of A, we should know what are the subsets of A, B and C, because this X is just not known. Let me therefore present before you the subsets of A, of B and of the set C. Suppose firstly we start with set number B. Set number B is A, B and C. What do you think are the possible subsets of this set? The first subset is obvious, the empty set. After borrowing nothing from set B and therefore creating empty set, the next step is to borrow one element from set B. And this can be done in three distinct ways. Either you just borrow A, or you just borrow B, or you just borrow C. After borrowing single element process is done, now we go again to B to take two elements at a time. And this can be done as follows. Either you borrow A and B, or you borrow B and C, or you borrow A and C. Once borrowing two elements from set B is done, now we proceed to borrow all three elements, and that will make B itself land in here as a subset. Once we have obtained all the subsets of set B, it is now turn to pack them all inside one set, and that set is called the power set of B. Doing the same thing with set C, which is given to us as B, D. This set C has how many subsets? Let's try and write that elaboratively. The very first set, as obvious, is the empty set, which is obtained by borrowing nothing from set C. After this, we go to set C to borrow one element, and that results in singleton set B and singleton set D. After that, we go and borrow two members from set C, and this makes C itself land up in here. Next step is again to pack them all inside one single set, and that set is called the power set of C. Now the question is saying find all X such that X is a proper subset of B and X is a proper subset of C. This means this X, which is a subset of B also and C also, is a common subset of both B and C. If it is a common subset of both B and C, it should lie in the power set of B also and power set of C also. Let's see which all members are lying in power set of B and power set of C commonly. The first set, which is obviously common, is the empty set. After that, singleton B is common in both power set of B and power set of C. Singleton D, that is not common. BD, not common. In fact, there is nothing else common. The only common sets are phi and singleton B, and therefore the solution of the first part is X is equal to phi or X is equal to singleton B. These are the possibilities that X has. X can be phi and X if it has to be a subset of B also and C also. In order to obtain the next solution, I want subsets of A which are not a subset of B. For that, we will have to do some hard work in obtaining the power set of the set A, because that is what is required. A has 4 members, A, B, C, D. Let me try and obtain its power set. The first step obviously is to borrow nothing, and therefore empty set comes as the first subset. Now borrow all possible singletons and you get 4 singleton sets. After doing this, go to A and take 2 elements from A. What does that give? It gives either AB or AC or AD or BC or BD and CD. These are the subsets which can be obtained by just borrowing 2 members from A. After that, we move on to the possibility of borrowing 3 members from A, and that gives me ABC, A, B and D, and A, C and D. After which I have B, C and D. These are the members which are obtained once we borrow 3 elements from A. This has given us an exhausted possibilities of borrowing 0, 1, 2 and 3 members from the set A. The only possibility left is borrowing all 4 members, which is going to make A itself land in here. Firstly, let us count if we are getting 16 subsets or not. How did I say 16? Because cardinality of A is 4, and we know if cardinality of a set is n, then number of subsets that is has, which means the cardinality of power set of A happens to be 2 to the power n, which is 16 in this case. And therefore A should have 16 subsets. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Once all the subsets are obtained, pack them inside one single set, and this is your power set of A. The second question is asking all the subsets of A which are not a subset of B. Subsets of B are all of these, and subsets of A are here. You can simply see which are the subsets which are subsets of A but not of B. Let me first start with B. Phi is here also. I am not interested. Singleton A is here, singleton A is here also. I am not interested. Singleton B, singleton C, I don't want. AB is here, BC is here. I don't want AB, I don't want BC. After that, AC is here and ABC is here. So I don't want AC and I don't want ABC. So what are you left with? You are left with singleton D, AD, BD, CD, ABD, ACD, BCD and ABCD. These yellow ticked sets are the subsets which are subsets of the set A and not of the set B. You can just collect them and put them inside a set, and this will be the possibilities for the second question and solution of that. Quickly note this down with full understanding, and then we will be moving on to the fourth question. After this particular question, fourth question is already waiting for us. Have a look at it. The fourth question is asking us a very tricky question. Let A, B and C be three sets. If A belongs to B, that means this A is not a set here, it is a member of B. Okay? And B is a subset of C. Here B is acting as a set. Is it true that A will be contained in C? If not, give an example. That means if I come up with something like A, B and C such that my set A is acting as an element inside set B and my set B is acting as a subset of set C, and obtain that A is not contained in C, well then this particular claim won't be true. In fact, it will be false. Let me show you such an example. Suppose I take my set A to be just a singleton A, okay? I take my set B to be this singleton A, which is the set as an element inside B, because that is what I want, and some other random member B. After which I take my set C to be singleton A, B and another some small c random number. You can clearly see that singleton A is a member of B. It is not a subset of B, it is a member of B. See, this is where it's sitting. And then you can also say that my capital A is a member of set B, because singleton A is nothing but capital A, and this first claim is very much verified by this example. Next, we have to verify if B is contained in C. For B to be contained in C, every member of B should be a member of C. We know that singleton A is a member of B, and singleton A is also a member of C. Wow! Well, just one more member to check. We have B to be a member of B, and my B is also sitting inside C. Therefore, B is very much a subset of C, and the second condition is also verified. Now we just have to ask these three sets whether A contained in C claim is true or not. What is my A? This is my A and this is my C. For A to be contained in C, every member of A should belong to C also. But which is the only member belonging to set A? Set A is singleton A. Only small a belongs to my capital A. But is small a member of C? Small a is nowhere to be seen. Singleton A is not small a. Singleton A is a set containing A, whereas only small a is just an element independently. Don't confuse small a with the singleton set containing small a. And therefore, small a does not sit inside set C. Therefore, my A is not a subset of C. Therefore, this particular claim that it is true is actually not true. It is false. This is the example which is that for this question. Note this down and then wait for the next question.